All right, so in this video here, we're going to be talking about derivatives and integration of the function e to the u or e to the x, all right? Because I don't know if you've seen this before, so a lot of the integration techniques that we're going to be learning later on, uh, you're going to see e to the x, and also you're going to see the natural log of x a lot. So I think it's really good if I just review it real quick. So first, let's just assume that we have the function f of x equals a to the x. So this is just your basic exponential function, nothing special about it. All right. If we wanted to find the derivative, then we can go ahead and use the definition of the derivative, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. Hopefully we all remember this and how dreadful it was when things started to get a little weird and you had a lot of algebra. But anyways, so because our function is a to the x, we're just going to write the limit as h approaches 0 of a to the x plus h minus a to the x all over h. Now, right here, all right, we can rewrite this as the limit as h goes to 0 of a to the x times a to the h. Let me write that nicer. A to the h minus a to the x all over h. This right here, what I did right here, that's just your product rule of exponents. That's all that is. I just rewrote it in a different way. Oops. All right. And as we keep going here, we can take the limit as h approaches 0 and factor out the a to the x to give us a to the x times the quantity of a to the h minus 1 all over h. Now, this factor right here does not depend on h at all. It's just a to the x. So, using our rules for limits, I'm going to just take that and I'm going to put it out front. Oops. So, we get a to the x times the limit as h approaches 0 of a to the h minus 1 all over h. Oops. Don't know why that happened. So basically you have this, all right, right here. And I know it looks a little weird at first, but the thing we have to remember is the limit is the value of the derivative of f at 0. In other words, what this is really telling us here, I'm just going to highlight it here so you know what I'm talking about. So what this is really saying here is the derivative at x is equal to the function, or the function's derivative evaluated at 0 times a to the x. So some of you may have seen that something like the derivative of e to the x actually equals just e to the x. All right, that's because e to the x evaluated at 0 is e to the 0, which is 1, times e to the x, which is e to the x. But I think this definition that we have right here, so I'm going to go ahead and put a nice red box around it now. So this kind of really brings it home. And the reason why is because the highlighted text, there is one special scenario or one special case. So we have one special case of the limit as h approaches 0 of a to the h minus 1 all over h. And that is the scenario where a is equal to e. So we can define e. And there are multiple ways to define e. But we define e as E is the number. Oops. E is the number such that the limit as h approaches 0 of e to the h minus 1 all over h equals 1. Okay? So there's a very special case right there. All right? And that is why when you were told a while ago, if if you were told this or maybe not, but that is why the derivative of e to the x equals just e to the x, okay? But this doesn't really help us when we have something like, let's say, what's the derivative of e to the u, all right? Where u is a function of x. So it could be, anything really. It could be like something like this example here, which is like find the derivative of e to the negative 4x. All right. Well, in this case, we need that chain rule. So anytime you take the derivative of any e raised to a function, you're always going to be doing the chain rule no matter what. Okay? So the chain rule is just right, it's the function times the derivative of u or just negative 4 times e to the negative 4x. That's what it boils down to. All right? So I'll do one more derivative of u, or I'm sorry, of e to the u, just so we can see how it works again. So find y prime if y equals e to the negative 4x times the sine of 5x. All right, so here we're gonna need the chain rule, and we're also gonna need the product rule. So y prime is gonna equal e to the negative 4x times the cosine of 5x times 5 plus the sine of 5x times e to the negative 4x times negative 4, which, if you notice, we have e to the negative 4x in both terms, so we could just factor that out to give us e to the negative 4x times the quantity 5 cosine of 5x minus 4 sine of 5x. And there we go. Now, the same thing applies when we were integrating. All right. So, in general, e to the x dx is equal to e to the x plus c. I mean, that's in general. But here's the problem. This is a very specific example. This is when, you have just a function of x and it's literally the variable x. That's it. Now the question becomes, what if you wanted to integrate, let's say, e to the 3x dx? Well, in this scenario, we are forced to use substitution. Okay? So we're going to let u equal 3x, du equals 3 times dx. And remember, I like to solve this for dx. So I'm going to divide both sides by 3. All right? And that's just going to give me this right here. I'm just going to rewrite this. It's going to give me 1/3 du equals dx. This way, when I go to make my substitution, wherever I see 3x, I'm going to write a u. And wherever I see dx, I'm going to write 1/3 du, which I know I can pull the 1/3 out front. And now the integral of e to the u is just e to the u. So this is 1/3 e to the u plus a constant, which is 1/3 e to the 3x plus c.